Good afternoon, everybody. Welcome to our Wednesday Compass seminar. Today's speaker is Samantha Kramer, a PhD candidate in our program. A quick bio on Samantha. Samantha was an undergrad at University of Miami, and then her major was in meteorology and applied mathematics, right, and minor in physics. And Samantha transferred to our PhD program once she got her Bachelor of Science. And so she's been in Miami for 9 years. So she definitely likes Miami. So I asked her what her favorite part about Miami is, and it's sports, the hurricane. Right? And good. Least favorite is not traffic. Samantha loves traffic in Miami.
Absolutely.
Right. Least favorite part about Miami is the lack of Italian bakeries.
Yes.
Right. No cream puffs.
No cream puffs.
Okay.
Yeah.
So Samantha is doing her PhD under supervision of Ben Kirkman and Paquitas Videma. She's giving a 1-hour seminar, which means that she is almost ready to graduate. And the title of her talk is Saharan Dust Variability at Miami, Florida. Okay, the floor is yours.
Good afternoon, everyone. I'm Samantha Kramer. I've, like you said, been here for 9 years, so I know most of you. My committee is co-chaired by Ben Kirkman and Bakita Zaidama. Also on my committee is Amy Clement and Fong Nagon from the Air Resources Laboratory. And I'm really lucky to have such a great group of people. And I'm going to be talking about Saharan dust variability at Miami, Florida today. A brief outline of my talk. I'm going to give a little bit of introduction and motivation. Talk about my first project here, which was analyzing Miami measurements and Mera 2 dust reanalysis. Then I'll move on to my most recent work on subseasonal variability of extreme dust events over South Florida, followed by my current and future work and an overall summary. And in general, I'm following this format with driving questions, methods and data, results, the questions that we have answered, and how many more open questions we have now. So just to get started on some background and motivation, here's a satellite image of Saharan dust over the Atlantic Basin. And it's always fun to look at a real image and kind of have that in your mind when you think about the science. So let's start from the basics. What are aerosols? They are small liquid or gas particles that aren't part of a cloud, being clouds, but they aren't cloud or precipitation particles. Some natural examples are sea salt, mineral dust, which would be Saharan dust, smoke from wildfires and volcanoes, and there's also anthropogenic sources such as smoke from biomass burning, black carbon, and sulfates. And as atmospheric scientists, we care a lot about aerosols because of the Earth energy balance. So basically, aerosols here interact with the radiative balance of our planet. Large aerosols absorb long-wave radiation, so radiation from the Earth can be absorbed by large particles. And then the small aerosols can scatter and reflect shortwave or solar energy and absorb energy from the sun. And they also interact with cloud processes. Since we have a lot of climate scientists in the room, or brand new climate scientists in the room, I'll talk a little bit about what that means. So you can see here Saharan dust from our satellite image over the ocean. So Saharan dust particles over the open ocean will actually absorb solar energy and can cause cooler surface temperatures, which is an important consequence. And we also have regions where the Saharan dust creates stability in the atmosphere because it's absorbing heat, so we have stability in the atmosphere. And we can have low-level clouds that really kind of get stuck under this layer and increase cloud coverage, as you can see by the second box there, where we have increased cloud coverage. And we also have a number of cloud aerosol effects that Saharan dust plays a role in, such as creating, working as cloud condensation nuclei, which can then create really, really bright clouds that last a long time, and these are all radiative factors that we care about. And specifically for the Saharan Desert, it is the largest global contributor of dust particles to our atmosphere. So as you can see, Saharan dust is of extreme importance to our climate system. And not only to our radiative processes, They also pose a human health risk. So Saharan dust particles are often smaller than 2.5 microns, which penetrate human lung tissue. They also add nutrients to soil and ocean surfaces, cool sea surface temperatures. In fact, a study found that 30 to 40% of anomalous cooling in the Atlantic was attributable to Saharan dust, and that's a pretty surprising value. And for all the hurricane researchers in the room, Saharan dust has an obvious effect on hurricane development, besides the cooler sea surface temperatures, including cloud seeding and, in general, dry air intrusion. So now that we know why we care about Saharan dust, let's talk about how it gets into our atmosphere. So surface winds over the Saharan desert kind of kick up all this dust into the atmosphere. And the dust is slowly pooled into the air over the Saharan desert. And this is creating a Saharan air layer, a warm, dry, dusty air layer. And this air is then ejected periodically off the coast of Africa in African easterly waves. So basically, modulators of the African easterly jet. You can think about it in terms of like fronts, where we have our jet stream and then we have frontal systems. Similarly, African easterly waves are just modulators of an African easterly jet. So we have periodic releases of Saharan air layers off the coast of Africa. Now, what do these look like? So we have the dry, warm, dusty layer, and the height, the thickness, the amount of dust in each one varies. But in general, they reach up to about 6 kilometers in the atmosphere, and they're above cloud level but have some interaction. And you can see here in this top image that a Saharan air layer has like a defined border. So it's its own air mass, separate of marine air. And there's a lot of atmospheric stability induced. We have a Saharan air front of dry, warm air that's separate from the marine boundary, the marine air. And dust particles are slowly removed by wet and dry deposition as the Saharan air layer moves west. And to talk more about this movement, because it is really important to my work, so we can see here from this image, a Saharan air layer is ejected off the coast of Africa, along with an African easterly wave in the trough, and it is then cut off by the ridge of the wave. It travels to the west along the African easterly jet, and it doesn't cross the equator. It's bounded on the southern border by the African easterly waves and the ITZZ. And in general, a Saharan air layer is a closed system. It deteriorates over time due to entrainment and mixing, but it in itself is its own air mass. So basically, based on the point of the talk, we receive these Saharan air layers and the Saharan dust in the summer months. So here on this plot is a dust record from Barbados in the Caribbean and Miami of annual or June, July, August average dust mass from 1975 to 2014. And we have a lot of year-to-year variability in Saharan dust. So it seems to be really important because there are so many different effects, but the variability still isn't well understood. And just to show some examples, Moulin et al. 1997 found the NAO and dust correlated at about 0.5, but then Reamer et al. 2006 found no relationship between the NAO and North African dust. Prosper and Lam 2003 associated major peaks in Saharan dust associated with El Nino events. But then if we look at more recent studies, no trend with the AMO. Doherty et al. 2012 actually found, again, no correlation with the NAO, almost no correlation with ENSO, except for the 1-2 region. And the most recent study, DeFlore et al. 2015, found that it was actually correlated with the La Nina. So there's no coherent message here. And all of these studies are based off the Barbados dust record. And Miami and Barbados, despite having similar looking variability, actually only correlate about at 0.3. So there's different processes there. And a lot of these studies look at averaging a dust index or an average measured dust mass or how much emissions to just the El Nino index or the NAO index, and not actually looked at the atmospheric dynamics involved. So the goal of my work here has been to go back to the basics. So just thinking about the problem, how can we change dust concentrations downwind? Well, we can change the surface winds over the source region or affect the soil moisture. So we can change the amount of emissions that are being released. We could change the wind vectors driving the transport. So If we change anything over here, we're changing emissions. If we change anything over here, we're affecting the transport. And we need to kind of figure out why these things change and what has the biggest impact. And also, what is the difference between Miami and Barbados? As you can see here, Barbados is directly west of the emission region. So anytime dust is pushed off the coast of Africa, it's a lot closer and it's going to get dust almost every time. But Miami here, we're located further away and more north, so transport is a much bigger factor for us. And is there anything that we can predict? And so with that, I'm going to move on to the first part of my research that I did here as a graduate student, comparing Miami measurements and the MERA 2 dust reanalysis. And I'm going to preface this with saying, in the summer months here in Miami, Florida, we breathe in Saharan dust all summer long. It's actually our largest aerosol contributor in the summer months, and this is sea salt. And in general, we are very lucky here in Miami. We have very clean air. So when we look at our aerosol environment, we only have two big contributors. So my driving questions for my first study was, what does the daily dust loading at Miami look like today? How well is dust represented in the MERA 2 reanalysis, which uses a new AOD assimilation process? And what is its potential for accurate impact studies and forecasting? And this was really driven by the fact that global aerosol models have been on the rise. A lot of efforts have gone into forecasting aerosols, and there's a lot of complex models that can only go about 5 days out. And previous studies of the MERA 2 reanalysis have only compared total aerosol optical depth, and they don't address vertical structure or the different species of aerosols. So let's talk about the Miami measurements. Here on the roof, right above our heads, filter sampling of dust has been done since 1974, and we revamped the project in 2014. And on the roof right above MSC, there's a lidar machine and 2 sun photometers, thanks to a grant that Paquita Zenema received. So we can take vertical images of the atmosphere above us, and we have daily measurements of actual dust concentrations here. I'm also going to note on this map that we only measure or actively take in dust measurements when the winds are blowing off the water, so we're not having any interference from mainland pollution. So for this study, I used the daily dust mass measurements or concentrations from 2014, 2015, and 2016. And we haven't changed the filter techniques or processes since they began in 1974, so we have a lot of consistency here. And we do have 17 size resolved days in 2016, so we actually can take the measurements of each individual aerosol as a group. And then the LIDAR, the instrument on top of MSC that I just spoke about, that measures particle asphericity. So basically, we have 2 main aerosols, sea salt and dust. Now, sea salt is really round, kind of like a ping pong ball, where dust is really awkwardly shaped, almost like a crumpled up piece of paper. And when you measure using a LIDAR, you can distinguish how awkwardly shaped each particle is. So we can tell what is dust in comparison to what is sea salt. So we can identify dust in the vertical. And just to talk briefly about MERA 2, it goes from 1980 to the present. And the aerosols are coupled to the meteorological reanalysis with emission, loss, radiation, and it does separate aerosol species, dust, sea salts, which is what we care about the most. And what makes MERA 2 different is that it assimilates aerosol optical depth from satellites to correct itself as it goes. Models inherently have this problem where they lose too many aerosols over time, so this was a way to kind of correct for that. The problem is they're only assimilating a vertically integrated aerosol optical depth. And then it's internal where they decide where to put them in the atmosphere, which species is which. So all of those are done internally and aren't actual individual measurements that are assimilated. And for MERA 2, I took the daily average, which is 8 time steps, 5 mass bins, and I considered the lowest level to be the surface. And lastly, as a preface, I just wanted to show the climatological dust season. We have here is July with the peak and slowly falling off into September. And here, 2014, 2015, and 2016, I'm showing where they fell on the map of average. So we had a lot of good variability between these 3 years that we looked at. We had 2015, which is really like a classic season. 2016, which was our lowest measured year on record. And 2014, that actually had a peak in August instead of July. So we captured a lot of variability just looking at these 3 years. Okay. So what does dust look like today? So we can see here, these are depolarization ratio. So the bright red, that is dust. We know that is dust. And the bars are daily dust measurements, so the filter measurements taken at the roof. And we can see that the majority of the seasonal dust arrives in just a few large events. However, there is at least trace amounts of dust almost every single day. So we have small amounts of dust every day, but the majority of our dust mass comes in these small episodic events. And you can see the variability between each year. So how well is this represented in MERA 2? Well, they get the distribution pretty well, the frequency of these dust bins. So when we have almost no dust, minimal dust, and then these few large events. So that is promising to see that they really captured this variability. But when you look at correlations day to day, MERA 2 actually overestimates the daily dust mass by about an order of magnitude. And so we had taken a look at the aerosol optical depth, since it's taking the overall aerosol optical depth, and we found that it actually overestimates the aerosol optical depth as well, but only on the low days. So, we believe that this is probably more of a sea salt effect, because sea salt is also extremely overestimated in MERA 2. But in general, we have 0.63 correlation with our daily dust measurements, and that is really good for a reanalysis, specifically for dust. It's just over by about an order of magnitude. And where we think that this is coming from is from our dust distribution by size. So MERA 2 dust emissions follow a skewed log distribution based on a previous study, taken in LACES. And so the majority of the mass from MERA 2 actually falls between 2 and 3.5 microns. And they have negligible mass in the largest size bin. So they are assuming by the time dust reaches Miami, all the large particles are gone. They've already fallen out. We don't have them anymore. But when we looked at our size resolve data, we actually found that we do receive a lot of these large particles. It is not negligible. And also, the majority of our mass came from the smallest size particles. So, with MERA 2 placing too much weight in this middle size range, that could be one of the causes of the overestimation of the dust mass. So we thought that was an interesting result. And lastly, we can look at vertical structure. This is an image from the roof at MSC. And we can see on average dust is present between 1 to 4 kilometers. When the Saharan Air Layer is ejected off the coast of the Saharan, it goes up to about 6 kilometers, but it slowly subsides as it moves. And there's a lot of layering of dust concentrations, which may be important for radiative processes. And when we look at MERA 2, so here's our layering and our observations. And MERA 2 gets the average height profile pretty well. It just misses these layers, which may be a problem for radiative studies. And also, if we look at the frequency of when by particle size, the actual smallest size particles are often lofted by convection in the model all the way up to 15 kilometers, which we didn't see in our observations. So there's also the possibility that some of these small particles we're not seeing at the surface because they were convectively lofted up. So what have we answered? Well, what does daily dust loading at Miami look like today? Well, it's present almost every single day in at least trace amounts. The majority of the dust mass arrives in a few large events each year. Concentrations vary with height and layers, and we're mostly consistent of small particles, less than 2.1 microns, but we retain many colossal sized particles greater than 10.2. And what have we learned about MERA 2? Well, it's pretty consistent with observations, and it represents the seasonal dust distribution pretty well. The room for improvement would be kind of the vertical structure, missing the kind of layering effect, the overestimation of dust by an order of magnitude, and the overall size distribution. And so we can answer what this means for potential accurate impact studies and forecasting. We can use MERIT-2 for annual monthly variability studies, and we can use it to look at surface measurements on the daily timescale. We just have to acknowledge, okay, these are going to be a little bit larger than what we see in observations. In terms of impact studies, since they are missing mass in the lowest size bin, that may have an effect on both radiative studies and health impacts. And some of our remaining open questions are, okay, we know what daily variability in the structure looks like. How can this help us look at our larger scale? Why is dust variability between Miami and Barbados different? So Miami and Barbados aren't really strongly correlated. And actually another study found that MERIT-2 was underestimating dust at Barbados, which is actually closer. And what happens between emissions and arrival? Which is kind of like this black box. So that brings me to my more recent work that was submitted to JDR Atmosphere last month on the subseasonal variability of extreme dust events over South Florida. So for this work, my driving questions were, is dust loading variability at Miami just random noise? Do we have these episodic events and it's just random? Or is there anything that we can look at and attribute to any atmospheric dynamics? And can we use what we know to predict dust loading without a complex aerosol model that can only go out to 5 days and is really computationally heavy? And I wanted to focus on dust transport because a lot of times we focus on the emissions or measurements at a given location, but what happens in between is kind of a black box of, well, it goes from here to here. And so that's the problem I wanted to focus on. And specifically, a concentration at any location is a function of emission, transport, and deposition. So if we emit dust here, we start with a value, we lose dust along the way in deposition, but it still has to end up in Miami. And previous work has shown that transport is the largest factor for the amount of dust that we receive here. It should also be noted that in general, studies have found dust emissions have been decreasing by about 10%. This has been associated with climate change and surface winds over the source regions. So that's something to keep in mind. And this may be the difference between Miami and Barbados, that Barbados is more emission dependent than transport dependent. And just to remind everyone about the climatology of the Atlantic Basin in the summer months, our dominating flow field is due to the subtropical high pressure system. So we have clockwise motion around the subtropical high, the ITZZ, and this is in general what our flow looks like. So what scales do we need to capture to look at subseasonal variability and to look at transport? Well, on average, it takes 10 days for dust to go from the coast of Africa to Miami. So we need to account for something on the synoptic time scale. But we need to also factor in daily changes because a Saharan Air Layer deteriorates and loses dust mass each day depending on how much mixing occurs. And we want to average over long periods of time. And spatially, we're going across the full Atlantic Basin, but we still want to account for things like mixing along the way. So for this work, I used a few tools. I used our dust mass concentrations from 1974 to 2016. I used NCEP reanalysis, and now everyone's saying, okay, you spent all this time looking at MERIT-2 reanalysis, why the switch? Well, NCEP actually goes back further in time, so I could use the full record that we have of dust. Also the high split model, which I'm going to talk a little bit more about, has very specific formatting, and they are gracious enough to pre-format NCEP files. So for those reasons, I started using NCEP for this work. And the high split model I use to run back trajectories daily, which I'm going to talk about right now. And I use all these methods to come up with a Saharan dust transport proxy. So that's where we're headed. I'm going to take a few moments to talk about high split trajectories. I think it's a really valuable tool. So basically we have an air parcel. We know where this parcel is at day 0, and we know what the velocity is at day 0. The high split model takes a first guess at its new position a few hours later, and then using the new position and the velocity at the new position, takes an average to get a final position. So we're just moving and tracking an air parcel backwards in time, or forwards in time, in my case backwards in time, using the velocity. It's simple, distance equals rate times time. And high split can be run at any grid size. It's based on the meteorology used. It uses, in my case, NSET meteorology, the zonal wind, meridional wind, and vertical winds. And of course, there are error bars. You can't say, okay, this trajectory ends here. This air parcel came within 1 mile of this location. It's more for general visualization of the flow. To give you an example of this, I have 296 back trajectories that I was then able to cluster into groups. So for example, this cluster shows a zonal flow pattern that is fast zonal movement across the Atlantic Basin. And this exact flow pattern happened 6% of the time. So this is just one of the things that I can do with the high split model. And just to show confidence in this method, I had run between 1989 and 2016. I ran this for every single day, and it represents the seasonal cycle really well. We had a lot of continental airflow in May. By July, we have full easterlies, just like our tropical meteorology, climatological winds. And then by September, we're starting to get more continental influence again. So it represents our seasonal cycle well. And also, we can take a frequency analysis of trajectories and see where the trajectories pass through most often. So for example, our highest dust year on record, we had a lot of zonal flow, almost correct, connecting directly back to Africa. And our lowest dust year, very few trajectories even made it back to the coast of Africa. So these are just a couple of tools that I used, and I'm happy to talk with anyone about high split model if you're interested in using it. In my case, I ran a high split back trajectory going back 10 days, so the length of transport, for every single day of the summer for 43 years, which was so much fun. And by doing this, I can account for daily changes because a new position is calculated every day. So I'm accounting for daily changes during the entire length of transport, so over 10 days. And I can analyze each trajectory, so I can analyze them in bulk, which is really what we're aiming for. And in my case, I'm using the highest and lowest dust cases. So what does that mean? Okay, so we have a lot of data. In order to highlight what is most important, I chose to look at the 15% highest and lowest dust days in both July and August. And you can see by just looking at the extremes, we have really good coverage over the entire month. So here we have the day of the month in each year. And we can see that we also often have consecutive days of extreme high or low dust. And in general, though, there's surprising amount of persistence each year. So if you look any given year, there's only high extremes or only low extremes. Even though they're clustered together, in general, there's persistence longer than the synoptic time scale over time. But how does this look compared to our overall dust mass? So if we take the number of highest dust days and subtract the number of lowest dust days in any given month, and we plot that against our average dust mass concentration, we have really good agreement. Actually correlates at 80.8. So this 15% threshold is really representative of our overall seasonal average dust concentrations. And I did test this as well with 33%, the top 33% and top lowest 33%, and all the results were about the same, just slightly less in magnitude. So feel really confident that because we're looking at episodic events that are persistent, that this method really captures what we need. So what do these look like? Okay, so at the top here, we have July and August, the 15% highest dust cases, and at the bottom, the lowest dust cases. And we can see in the highest dust cases, the thick black line is the frequency, so where trajectories pass through the most. That we have generally fast flow. So in general, when you go from east to west, the air is moving about 6 degrees per day, which is pretty fast in comparison to the lowest, where in general, trajectories don't go back as far in the same 10-day period. It's only about 3 degrees per day. So in general, for highest dust cases, we have faster zonal movement, and also each individual trajectory doesn't move much in the meridional direction. In the lowest cases, almost no trajectories go all the way back to Africa, and each individual trajectory travels much more in the meridional direction, indicating there's more air mass mixing. Similarly, I had run a cluster analysis on these, and for the highest dust cases, we only had 2 clusters, so only 2 wind patterns, one in which the trajectories go all the way across, and one where they stop about here, so almost the exact same airflow. But in the lowest cases, we had 4 trajectories, one that traced back easterly, one that went around the continental US, one that came up from the middle of the Atlantic and from the south. So there's a lot of different airflows. So we can say that these are 2 distinct air patterns, where the highest dust cases has a distinctive airflow. So now that I know that they're different, I can just take the difference between the 2. So this is the highest minus lowest cases of 10-day averaged, so during the transport period, of zonal wind, meridional wind, and geopotential height. And we can see that we have increased easterly movement, across the Atlantic Basin, especially after 45 west. And we have increased meridional flow up the Florida Peninsula for the highest dust cases. Also, this is following geopotential height anomalies, and these are associated with a movement of the subtropical high. So our highest dust cases have increased zonal flow across the basin, increased flow over the Florida Peninsula, and this anomalous flow is associated with movement of the subtropical high. So we can look at a Hofmahler of these plots. So just to explain, so this is longitude, so over here would be Africa, Miami is about here, and day 0 would be the day of we recorded a high extreme, the day that we recorded a low extreme. So right here is where our air mass starts, and that up there at the top is where we took our measurement here at Miami. And so if we look at the zonal winds across the basin, we see that there's a propagation of a zonal wind anomaly. So we have increased wind speeds propagating across the Atlantic Ocean, across the Atlantic atmosphere. And when we look at the meridional wind over the Florida Peninsula, we have a burst of southerly winds right before our measurements. So that would be right here. So right before we measure our high dust extremes, we have a burst of winds that come up the Florida Peninsula. And just to mention, for this propagating easterly flow, it has been previously suggested by Cardian-Pudi and Carlson that the dust in a Saharan air layer makes a thermal wind imbalance and actually helps to propagate, increases the African easterly jet, so it actually increases the easterlies itself. So there is a chance that the Saharan air layer itself is contributing and self-propagating, and that's a remaining open question. How much of this is actual background flow and how much could it be self-propagation? So, and how do we attribute this anomalous flow? So if we look at, again, the highest and lowest cases for the subtropical high, we can see in the highest cases, the NASH has moved south and is displaced west. So we're having increased easterlies in this region, and then as we have our clockwise flow, we are causing there's wind flow up from the south directly over the Florida Peninsula. So you can imagine the airflow is coming here, and right as it reaches Florida, it's coming back around. But for the lowest cases, a lot of, on average, the NASH is over the Atlantic. So a Saharan air layer will come up and miss Florida and mix out over the Atlantic. And you'll notice there's a few cases where we have an extreme western border of the NASH. And these are cases in which a Saharan air layer travels zonally and then mixes out over the Gulf of Mexico. So this is our persistence factor. So yes, it's a synoptic case where we have zonal propagation and then a fast southerly wind component, just like our events, episodic events that we saw in our extremes, but we can attribute this to the North Atlantic subtropical high. And okay, so now, how do we know this doesn't happen just randomly? I ran a Monte Carlo test with random chosen dates for each data set and found that there was no signal unless I'm using the dust days. So this is promising that this pattern that we're seeing of increased easterlies and meridional flow is specific to our dust cases. I'll make a quick note here on precipitation because I know everyone always asks about it. It was not the focus of my study. I chose to ignore wet deposition because it's overall about 20% of a factor, and there's not variability is in the tropics but in general, if we look at the highest and the lowest cases, there is almost no difference over the Atlantic. So in terms of wet deposition, there's almost no difference between highest and lowest dust cases. If anything, we have a drier Southeast United States, also associated with the NASH moving, which would, if anything, result in less deposition of dust. So less dust coming down to the ground, carried by rain. And there was no shift in that ITZZ. So let's talk about predictability. So we've identified two key regions that bring us the most dust, the most important two atmospheric flows. So we have meridional winds over the Florida Peninsula and the zonal winds over the tropical West Atlantic. And bringing it back to the Pythagorean theorem, just because it's science doesn't mean it has to be complicated. So I just used the Pythagorean theorem, made a triangle, using these two data sets, and I averaged between 850 millibars and 500 millibars because that is our steering range for a Saharan Air Layer. And I averaged them across July and August for each year. So here's my dust transport efficiency. And we can see that there is actually pretty good agreement each year with our actual measured dust amounts. Correlation is about 0.2, which seems a little bit low, but if you break it down by decade, we actually have a lot higher values per decade. And if you look at July and August individually, the correlations go up even more. Now, keep in mind, this is not including emissions, and we are not including deposition at all. This is purely atmospheric dynamics, purely transport. So to have that good of a correlation is pretty promising. And let's note that we have had decreasing dust mass over time. So we've had less emissions. This has been showed in many studies. So we expect that we have less dust here. There's less being emitted. But our dust transport has actually been increasing in efficiency. And a number of recent papers have shown that the North Atlantic subtropical high has been trending westward with climate change. So there's possibly a more favorable wind flow pattern for dust transport over the last few years, last few decades. So this is promising. So what have we answered here? Is dust loading variability at Miami, Florida just noise? Well, no, I don't think so, because we have linked it to two key regions, the tropical West Atlantic zonal wind and the Florida Peninsula meridional wind. And these conditions are attributed to southern and western shifts of the North Atlantic subtropical high. So we have dynamic features that are linked to changing dust mass each year. Now, can we predict dust loading without a complex aerosol model? I will put this under the maybe category. So the DTE calculation is a good seasonal indicator of dust, and even better at the sub-seasonal scale. And we're not including emission or deposition at all. And dust mass has been decreasing over time, but the DTE has been increasing, possibly due to the NASH movement. So, open questions. Well, there are a lot more. So can we use this DTE to forecast using forecast models? Case studies to determine the success rate of the DTE. Also, readjust the relative dependence of transport is more important than emissions, which is more important than deposition. So there is really only one study that says this. So it's probably important to reconfirm. Will including an emission index add to the predictability? Is the Saharan Air Layer adding a self-propagation factor in that easterly propagation? And how do the various climate oscillations affect the zonal wind, the meridian wind, and the North Atlantic subtropical high? All of those previous studies had small or contradictory correlations, but maybe it's all related to how they affect the subtropical high. So that brings me to my current and future work. So currently, I'm working on can we predict dust at the sub-seasonal scale using forecast models and the DTE index. So multi-model ensembles are very popular right now, specifically the sub-X, sub-seasonal model ensemble, and the North American multi-model ensemble. So by using these, can I say that we know anything about the upcoming dust seasons? My current approach is to calculate the daily DTE value using reanalysis to determine a baseline. And then I'm going to be using the multi-model ensembles to give a lead week 1, 2, 3, and 4 forecast. And to determine basically if this is a useful predictor or not. Currently, my first tests are using the sub-X RSMAS model ensembles, which are 3 members at 850 millibars between 1999 and 2016. And I'm still using the NCEP reanalysis. And hot off the press, the first figures have finally worked. The dashed line is our daily measured dust mass. The black line is the NCEP reanalysis DTE. And then we have each model ensemble. So this is week 1. So this is what the forecast is 1 week away from when the initial product came out. 2 weeks out, 3 weeks out, and 4 weeks out. So these are brand new. So at first glance, first of all, the DTE does do pretty well with daily dust mass. We do get some of the peaks and the overall spread. So we have low dust mass increasing in a peak and then slowly tapering off. So that's promising. And in week 1 and week 2, the subseasonal DTE calculation is really in line with what the NCEP reanalysis showed in terms of growing and falling off. But by week 3 and week 4, we've lost almost all variations in DTE. The tropical weather in general is really small. We don't have huge pressure gradients. We don't have huge changes. So perhaps we just don't have enough variability to have any information this far out. So I'm going to say currently with just this one test that just started to work, I'm going to say week 1 and week 2 is looking promising so far. Week 3 and week 4, not so sure yet. But I will say, again, this was the first test. There are many models, there are many ensemble members, and this is only using the DTE index. I can also look at other variables. There may be an inherent lack of variance in the models for tropical summer. And there may be a large difference in the models and what heights I'm using. I still need to establish a DTE baseline using reanalysis, also test the longer seasonal model predictions and determine an create an overall probabilistic forecast. And so in summary, Saharan dust at Miami, Florida is present every single day of the summer in trace amounts. Most of our dust mass comes in a few episodic large events and vary in height with layers and mostly consists of very small particles, but we do actually get some of these very large particles. The high dust extremes that we get here are linked to tropical winds increasing over the tropical West Atlantic and the increasing winds over the Florida Peninsula. And both of these conditions are attributed to a southern and western shift of the NASH. And our DTE calculation is a good seasonal indicator of dust, better at the subseasonal scale. And this is without including emission or deposition. And it may be useful for predicting dust mass in the future. And overall dust mass has been decreasing, likely due to lower emissions. But the dust transport efficiency has been increasing, might be due to the NASH trending westward. And it's important to note that we've seen decadal oscillations in dust emissions in the past, So if we go to another upswing of emissions, but our transport has gotten better, we may actually exceed our previous limits. But there's a lot of open questions still. But I'd like to think we know more now than when we started, hopefully. So we still don't know a lot about the differences between Miami and Barbados. Maybe Barbados doesn't matter about these tropical Atlantic winds. And are the small correlations between dust and known climate oscillations related to the North Atlantic subtropical high? I still need to readdress the relative dependence between transport, emissions, and precipitation, the possibility of including an emission index. Can we even define an emission index based on atmospheric dynamics alone? Self-propagation of a Saharan air layer, and whether or not dust emissions will change and how that will interact with our dust transport increasing. And with that, I will take any questions. Questions?
Well, there are some papers out there that relate emissions to the surface winds over Africa. So maybe it wouldn't be too hard to come up with an emission proxy.
Yes. So I did take a few first passes at that, like just taking the average wind speeds over the source region for a month. And at that time scale, there was like no wind, there wasn't enough variance to really say anything about it. So I need to go back and look at it in maybe a more smaller discrete timescale, possibly like a 15% or a highest emissions versus lowest emissions, and really dive more into the smaller timescales to identify what's important. Because when I just looked at the overall wind speeds at the surface, there wasn't enough variance to say that this is more likely or this is less likely at any given time at a month out.
So is the emissions really just driven by the wind speeds at the surface, just kicking up more sand?
Wind
dust?
speeds, some soil moisture as well. It's the low-level jets that really kick up the most of the dust, and then with the lower boundary layer, they kind of get stuck there, and then eventually it builds and builds and builds before being ejected off. So. And that is mostly driven by the heat differential. So when we change anything about the heat differential, we're affecting the low-level jets, and that's causing a decrease in emissions currently from the most recent publications that I've read. Anyone else?
So I saw that you looked at the movement of the NASH. Is there any way that NASH intensity could also maybe increase the zonal wind across the Atlantic? Because that was one of your main factors for bringing the dust to Miami.
Yes. So there have been a few papers that talked about intensity. I used just one contour to just kind of define where the extent of it was, and I haven't really looked at intensity yet. That is also an open question. I would assume the more intense or the larger pressure gradients they are, the faster wind speeds you will get. So there may be a factor there that I just haven't taken into account yet. So that is on the to-do list.
How long does it take for the dust to travel through the Atlantic?
Across the Atlantic, about 10 days on average.
So it's a weird question. So if it's only takes 10 days, how do you have a predictability beyond 2 weeks?
Yeah, so how do I have a predictability about, so that goes back to when I looked at the cases, each individual case. In fact, let me bring that up. So when we look at each individual case where, okay, this was an emission peak, this is an emission, arrival of a Saharan air layer. But if we look each year, there's persistence. So we don't have extreme peak, extreme low, extreme peak, extreme low, extreme peak, extreme low. But rather each year we're kind of dominated by highs, or all lows in general. So there is a persistence beyond just the synoptic timescale, which is why we think it's possible to predict at a longer timescale.
In the very beginning, you mentioned that you do measurements only when you have the winds blowing from offshore.
Mhm.
So what would be the windrows? Because you say that the dust is present every single day. Do we have days when the wind is blowing from the land only and it would be
Yeah, so the pump is only active when they're in the sector. But we do have a 10% threshold. So the airflow has to be coming in at least 10%. We have to have 10% of the day covered, at least, in order to count as the day having measurements. So yes, there are holes where we don't have data because there wasn't enough measurements. There wasn't enough time measured, but we do use a 10% threshold. So in the 24-hour period, if the air pump wasn't on for 10% of the day, then we would say that there's no data for that day, which is actually pretty rare. And generally, we mostly have easterlies, especially since we're only looking at the summer. I think maybe over the 43 years, there's like a handful of days where there's no data. So it's actually quite rare. And that standard was established by Prospero in his papers in 1999. So we've kind of just stayed consistent with what his protocol was.
Could it be some days when you may have a lower like sea breeze circulation versus a larger scale circulation coming from?
Yeah, so the amount of time measured does change day to day based on the winds. And that's just an inherent problem when you're doing in-situ measurements. Not every day is the same, which is why we have that minimal runtime. And yes, there is variability day to day, but we also, when we take our mass measurements, we are normalizing over the total amount of airflow that came through. So we're not averaging over, just the 24 hours. It's normalized by the amount of actual air that came through. So in a way, it's standardized without. We try to minimize the effects of how long it's been on.
Different question. So on a larger scale, do you think of the aerosols more just as sort of passive thing that just sort of moves from east to west? Or do you think of them as maybe having sort of through the change in the radiative properties in the atmosphere, does that affect the dynamics in some way and perhaps the structure of the subtropical high?
Yes, so there was, going back the other way, there was a previous work by Predictably and Carlson that I talked about, and they basically suggested that the actual dust particles in a Saharan air layer, they absorb so much of the heat that they induce a thermal wind that actually adds to the African easterly jet. So the actual dust itself is increasing the easterly winds. And so that's why I kind of left it as an open question, how much of this eastward propagation is self-propagated? Yes, we have the synoptic conditions, but there is the possibility that just by having a lot of dust for one of these events, that we are moving faster because of the dust, because of the thermal wind. And that's definitely an open question, something that would be really interesting to get into because it hasn't been, that paper came out in the 70s, so it's kind of fallen off into no man's land as an open-ended question. But I would be really interested to see if how much the dust actually influences its environment on those scales.
Yeah, what one could do, although maybe more postdoctoral work, is initializing the sub-X models with different amounts of dust and then seeing the sensitivity.
Yeah, model studies would be interesting. I can also run concentration runs with high split where you can prescribe the amount of particles that are released and look at how they move forward in time, which I've done a little bit of. And I know you do have the option to add radiative properties in there as well. So I can also use some of those to run some simulations. That is also, kind of open future current work to be done. Any other questions? All right, thanks guys.